Hello, welcome to finding the derivatives of log functions and the derivative of exponential functions. Most of this section is simply just memorizing derivatives. And so in this next couple of slides, I'm going to show you the derivative and the use of the chain rule with the derivative. So the derivative of natural log of x is simply 1 over x. Then if we use chain rule, it would be 1 over u times, of course, du dx. The derivative of log when it doesn't have a base of e is 1 over x natural log of a, where a is whatever the base is. And of course, this is what it looks like using chain rule. The derivative of e to the x is e to the x, and using chain rule, it's e to the u du dx. The derivative of a to the x is a to the x natural log of a. And again, we want to use that same thing with chain rule. Similarly, the integral of 1 over x dx is the natural log of x plus c. So just recall from previous courses the properties of natural log function. Its domain is 0 to infinity. Its range is negative infinity to infinity. It's a continuous, increasing, and one-to-one function, and its graph is always concave down. These are some properties of logs you may want to recall. We don't use change of base formula too often, but there it is. Okay, so we're going to use log properties to simplify. Again, this isn't really not calculus. This is a review of Common Core, I don't know what, Math 3, Math 2. But basically, the first thing we want to do here is rewrite this as the natural log of a minus 1 raised to the 1/2 power because of the property. And then the power property says that the 1/2 will drop. For the second problem, we're going to use both the power rule and the product rule. So we're going to start by separating it into two different logs, and then we're going to use the power rule on the second log. And that's your answer. So once again, if you want to pause this, and we're writing this now as one log. So if it's subtraction, it's going in the denominator, and if it's addition, it's going in the numerator. And remember, coefficients become powers. So the first one would look something like this, where the x plus 1 and the x minus 1 are both in the denominator because we're subtracting them, and then the 2 for the coefficient became the power. In the second one, the x minus 1 would go in the bottom, but the x plus 1 would stay in the top, and then we would raise that to the 3/2 power. And of course, we could also write that as that quantity cubed and take the square root of that. Okay, so to find the equation of the tangent line, now we're doing some calculus. So in order to find the equation of that tangent line, we have to find the derivative of this function. So to find this derivative, the first thing I want to do is start by rewriting the natural log of x squared as 2 natural log of x. So rewriting that, I can then use the product rule to find the derivative. So I kept sine 2x the same, and I took the derivative of 2 natural log of x, which was 2 over x. Then I kept 2 natural log of x the same and took the derivative of sine 2x, which was 2 cosine 2x. Once I have the derivative, then I can just simply evaluate the derivative at 1. And once I have the derivative, I have a point 1, 0. I can write the equation of the tangent line. And of course, I don't have to write 0. Okay? So in this one, we're finding the derivative, so we're going to have to use chain rule. So we have to find first of all, the easiest thing to do would be to rewrite this first problem. So I'm going to rewrite this because of the square root. I'm going to rewrite this as 1/2 the natural log of x squared minus 4. And I'm just using properties from Math 3. Then I'm going to use chain rule to take the derivative. So the derivative of the inner function is 2x, and the derivative of the outer function would be 1 over x squared minus 4. For the second problem, I'm going to have to use chain rule once again, so I take the derivative of the inner function, which is 1 over x, times the derivative of the outer function, which would be 1 over the natural log of x. Okay, so this one's a little bit more complicated. We have to locate any relative extrema and inflection points. So I'm going to start by locating the relative extrema. And we know that we do that first by finding the derivative and setting the derivative equal to 0. To find the derivative of this, I'm going to have to use quotient rule. And once I find the derivative, then I set the derivative equal to 0 to find my critical points. Now, to get that equal to 0, what I did was 1 minus natural log of x is equal to 0, and then I solve for x. So I have the natural log of x is equal to 1, and then I did e to the 1 is equal to x, and I got x equals e. Now, to test that to see if it's a local max or a local min, I have to do a sign chart. The reason I have 0 there, because my domain of this function is going to be x has to be greater than 0. It has to be greater than 0 because the natural log of x can only operate on positive numbers. And it cannot be 0 because of the denominator can't be 0. So my domain is going to be x has to be greater than 0. So evaluating this, I see that between 0 and e, my function is positive, my derivative is positive, and from e to infinity, my derivative is negative. Therefore, e is a local max. And to get 1 over e, of course, I just evaluated the original function at e. Now to find points of inflection, I have to take the first derivative that I obtained and take the derivative of that. And once again, I'm going to have to use quotient rule. That is the simplified version of that, but basically I use quotient rule to get it. Then once again, I have to set that equal to 0. And using my Math 2 skills, I get that x is equal to e to the 3/2. Then once again, I'm going to set up a sign chart. And I see that this function is concave down from 0 to e to the 3/2, and it's concaved up from e to the 3/2 to infinity. And e to the 3/2 is my point of inflection. And again, I evaluated the original function at e to the 3/2 to get the y-coordinate. Logarithmic differentiation is a method that we can use to differentiate a very convoluted function. So looking at this function, if I were to take the derivative of this, I would have to use product rule, and I'd have to use chain rule, and it would be very convoluted. But if I rewrite this using logs, so what I'm going to do is I'm going to take the natural log of both sides. Then I'm going to take the derivative of both sides. And when I do that, I have to remember to use implicit differentiation. So the natural log of y becomes y prime over y. Oh, okay, I'm sorry. The first thing I did was I rewrote it using natural logs. So I just simply rewrote this function. I took out the 1/2 because that was the power. And then I wrote it as the sum of the logs. Now I'm going to take the derivative of that. And I get y prime over y equals 1/2. And just remember the natural log of the derivative of the natural log of x minus 1 is simply 1 over x minus 1, so on and so forth. But I'm not done because now I have to solve for y prime. So to solve for y prime, I'm going to multiply both sides by y. But I don't want y in my derivative, so I have to replace y by the original expression. Ta-da! Now you may think that's convoluted, but think of how convoluted it would have been if we had tried to use product rule and chain rule on that. Let's do this last problem. So we have, we're going to start by taking the natural log of both sides. I think I can do this.